Okay, looks like everyone has this very clear to them, so which is a good thing. And I am glad you could already see a sneak peek into visualizations in Python, but we will have a deeper dive in just a while. So, all right, we start with NumPy now. NumPy, some people call it NumPy as well. I'm not getting into that, but NumPy, it's numerical Python. The full form is numerical Python. It has all the kind of math that you might want to do. You can create, but NumPy is basically known for its premium product, which is what? Which is arrays. Okay. NumPy comes in with a premium product called NumPy arrays. Be it one-dimensional array, two-dimensional, three-dimensional, multi-dimensional. People call them tensors as well. So NumPy comes with that utility, and basically the entire plethora of solutions, be it machine learning or whatever, they all somewhere down the lane they melt down to linear algebra. They melt down to calculus. They melt down to trigonometries and computations, etc. Everything, be it whatever, you can find that in NumPy, as long as it is mathematical or numerical. Okay, so that's NumPy array. I mean, if you store a list, and we will see the magic and the problem with the lists, you will see. And why I've written the flash here, because NumPy is NumPy is a package which is pre-written in the background. It is executed in Python, but the source code, if you see, it's written in C++, which makes it supremely fast. Okay. So what I would like to tell you is, if there are two possibilities, one in pure Python and one in the same thing in numerical Python, which is NumPy, always do it in NumPy. You will not realize when you are initially learning things, because the time that you are saving will not be that much for you to realize. Even you will not realize what is the difference between 1 seconds to 2 seconds. But when you work on big data, when you are working on the cloud, for example, when you are working on humongous data sets, there you will realize how much these things matter, how much it is important that you use efficient programming, not in terms of just the way you write a program, but what tools that you pick up to solve your problems. So always try to use NumPy as far as possible, because as the data sets get bigger and bigger, the time that NumPy solutions they take, it is very, very less as compared to normal solutions. So it has basically all the good things about it. Okay, you might need to explicitly create arrays, or use those syntaxes, but you get used to it. This is a habit that will eventually make you a great data scientist. Okay, so NumPy is your go-to tool. Even if you do not remember much of the stuff about lists, etc., if you remember NumPy, and if you have NumPy really fixed in your brains, you are going to be doing great in your Python career. And if you need more resources to learn NumPy, we have an entire playlist on Petroleum from Scratch YouTube channel. So after this session, you can go and check that out, because something that I might not talk about in this session because of the constraint of time, you will find much more details over there. All right, so let's start. Uh, if you have an option to choose between NumPy and others, choose NumPy. Okay, always choose NumPy. So let's start with examples one by one. So always you will have to import a package, because NumPy is a package, right? It's a package, as in it is a collection of various things, various powers, various functions. So you'll have to import NumPy with a pet name, which is NP. Okay, and now on you will be using NP in place of NumPy. The name of NumPy has now been changed for this particular code to NP. You can use whatever, NP underscore 123. That can also be used. Okay, this is your choice, but normally this is standard convention to use NP. Okay, now Let me show you a drawback of a list first. Okay, for example, my numbers. We created a list of range of numbers, right? Range, let's say 10. Okay, what is my numbers? Suppose you wanted to square these numbers, and if you do it using this will not work out. Okay. Yes, you can do it. We saw how we could do it in the session about for loops. We could, iterate over multiple things, multiple values in this list and square them up. Okay. One good thing I can tell you is a shortcut, which is a list comprehension, which is a combination of list plus for loop. It's not important, but just if in case I wanted to pick one element at a time, square them up in the list and replace them, or create its own list, how can I do that? So focus on this. N to the power 2 for n in my numbers. And I can store that as my num squared. Okay. So you can see this is a list comprehension. You have created a list using a for loop. You are telling the applied logic that, hey, I want to square a number n. And what n will be? N will be every number in my numbers. So this is called a list comprehension, which is a shortcut statement for a list plus a for loop. Okay. But the problem still lies in the fact that we are using for loops and lists together. So let me tell you one thing. For loops plus lists are the slowest combination. Okay. If you're using a for loop and a list together, you are making your program dreadfully very slow. You can try to skip it. Just don't do it. Okay. Because right now this is just 10 numbers. That's why it is being very sweet. But if you had, let's say, 10 million numbers, your program will freeze. Okay. And that's very common in data science. So now I'll tell you, what if I converted this my numbers to an array? Okay. My numbers array. The way to do that is np.array is a function, np.array. Okay. Because we are using numpy's part of array, that's why np.array. Array is a function in itself which is stored inside NumPy, just similar to this myfuncs package that we created. If we had to use the squarer new from myfuncs, we had to use myfuncs.squarer new. Similarly, we are using np.array. NP is a collection. Array is a function within that collection. And what we are passing to this is my numbers list. Now my numbers array, it looks like this. Now to square it, what I have to do is my numbers array to the power 2. That's it. And it took way less time. Okay. It took way less time. Let me increase the size of this to, let's say, 10,000. Okay. And this is, I don't have to print it. So check it. This will give us an error anyway. We know all that. But let's do that using a list comprehension and just focus on how quick or how slow it is. Okay. If I run it, you can see right now it is still very fast. So let me increase it by 2 zeros more. Okay. You can see it did take 1 second or at least half of a second. Let me add 2 zeros here as well. You can see even creation of list is taking time now. Okay. Even creation of a list is taking time. So you can see it just froze. It is running me out of all my RAM and is making my computer very slow. Oh my gosh, this is not responding. Wow. So you can see it took just to create this list. It took so long. If I run this, my entire program will go nuts. OK, it will not even work well. So I cannot take that risk. But if I convert this to a NumPy array now, OK, for creation of the NumPy array, it might take some time, but just focus on the computation time that it takes when I square it up. OK, just focus on that. Let's give it 1 minute. OK, it did get created. Now let me square it up. There you go. It did not even take 1 second completely just to square things up. And if I had run this, I would have to come back to the session after ending this session because my entire computer would have run out of RAM. So that's the benefit. I cannot emphasize enough on the benefit of using NumPy. That's solid now. Okay. Let's move on to see more and more examples about NumPy, and we will have our understanding solidified, and then we will move on to further packages. Okay. So, right. So there are a few functions in NumPy. There are a few ways to create an array by default. You don't have to, just like we had a range function in default Python, we can do that in NumPy as well. And just not squaring things, okay? We can also do this np dot sign of my numbers array. Okay. Now every time I use the my numbers array, it will take a bit of time because that's a huge, that's like actual data science sizes. So let's reduce the size, otherwise we will keep on getting stuck in the problem. Let's reduce it to 1000. Okay, now np.sign my numbers array. You can see you can also do the sine theta, you can do the cos theta, you can do the tan theta, you can do whatever. So you can assume this my numbers array to be the x-axis, and you are calculating y as a function of x. So this is a f and this is x. So y is a function of x, and you can store it to be y equals to whatever. Okay. So now this is y equals to fx, and you can do the plt dot plot my numbers array, which is the x-axis, and y, which is the y-axis. And you can see this is how the tan theta is executed. You can do the np dot cos. Okay, and you can see because we have a lot of numbers here. Let's use a smaller array now. Okay, let's use a smaller array. np, the way to create an array, just like we had the range function in pure Python, we can create an array in NumPy using this function np dot arrange. It's just the range function. The A is telling you that it will create an array, not a list. Okay, so the input parameters that go inside it are the starting point, the stopping point, and the delta x. Okay, so we can create an array like, hey, I want to create an array from -10 to 10 with a delta size of, let's say, 0.5. Okay, and I can store that as x or t, whatever. Okay, I can create a t array, and now I will do the np.cos of t, and I can do the plt.plot. Sorry, I can use the t here. X-axis is t, y-axis is y, and you can see now it is looking more like the cos theta we all know about. Okay, so this is all about how to create a NumPy array using dot arrange. Okay, let me tell you few more ways to create the same thing. np.arrange. This was np.arrange start, stop, step. Okay. And we will look at visualization simultaneously as well, and then we will have a look at a separate session of visualizations as well. There's one more way to create arrays, np.linspace, np.linspace, linearly spaced values. So np.linspace will have the same thing. It's just something we are doing the same thing as np.arrange, but rather than providing the delta x, we will provide how many number of data points you want to create. Okay, so I can type it like start, stop, number of data points, n points. Okay, basically it is one way or the other, they are both the same thing. Okay, so we can create t1 like this, np.linspace -10 to 10, and let's say 10 data points. Okay, and I can do the plt.plot t1 comma sign of t1. And I want to tell you some observations here. np.sign, I'm sorry. So you can see how terrible a sine theta function is looking like. The reason it is looking like that is now if I do a scatter plot, you can see there'll be 10 data points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's the reason the sine theta is not looking that smooth at all. Okay, this is plt.scatter. Let me color it to be red, and we can do the plt.plot on the top of this plt.plot. Let me remove the color to be, let's say, K, which is a substitute for black color. So you can see that's why it is looking so bad. Now, if I increase the number of data points to, let's say, 20, it gets a bit more smooth. The data points have increased. If I increase it to, let's say, 50, it will get even smoother. You can see now it's getting smoother, and the number of dots have increased. If I increase it to 500, you can see now we have a absolutely continuous sine theta plot. So this is all about continuity. Okay, just an observation. All right. Like I've told you, you can do all the computations multiplied by 2. It happens. It does not repeat. It just multiplies every term with 2. So let me tell you one concept here. Any computation you do in NumPy, does that computation on each element. Okay. So this is important because we are squaring things. So square will be applied to everything. If you are taking a sine theta, it will be applied to every element. So each element. So that's one way. That's one very important concept. Okay. So how about we create a two-dimensional matrix, 2D matrix in NumPy. So you can create it using this np.array. One simple way is to, for example, if you want to create a two-dimensional matrix like 1, 2, this is one row and this is another row, 3, 4, and you can store this entire thing within a square bracket. So a list of a list, this becomes a two-dimensional array. You can see a two-dimensional array, two square brackets. They tell you that it's a two-dimensional array. Check the shape of it. You can see 2, 2. Okay, and you can store that in a 2D. Now, the reason NumPy is so popular is because you can do something like this. np dot linear algebra dot inverse of area of array 2D. And you can see just one quick run and it gives you the entire matrix inverse. And you might already be understanding where this is important. It is important in solving a system of linear equations. All you have to do is store all the coefficients of that linear equation system inside a NumPy matrix and inverse it and take a dot product. You can also take a dot product. For example, this is a 2 cross 2 matrix, right? So suppose I had a x, or I had a b as, sorry, b as np.array. Ax equals to b, right? I can have a b as 3, 4. And I can take the dot product with b. And you can see this is the final values of x and y. x1 or x2, whatever. So this is just a way to solve a system of linear equations using NumPy's linear algebra utilities. Okay, so everything that you think about in matrix algebra, it is possible in NumPy. Okay, so that's about NumPy, and a few more things can be done, but we can save that for your own reading. We can also create a random default arrays like this. Default arrays like np dot zeros, a matrix of zeros, just like a placeholder. You can provide the shape of that shape to be, let's say, 10 cross 10. And you can see 10 cross 10 zeros has been there. So you can do the similar thing for np.once. And this can be useful. This can be very useful in the cases where, for example, if you are trying to write a reservoir simulation code, you would want to initialize the entire set of grid blocks of your reservoir with some initial pressure value. So you can multiply that by, let's say, the initial pressure value. And now every grid block has been assigned the initial pressure value. So like I told you, every time I will give you an introduction to a tool, I will tell you the kind of fast forward example that you might want to use it at, right? So this is about np.shape. Let me reduce the size to 3x3. Okay. So this is about np.once. You can also create an identity matrix, np.I, and it will not ask for two dimensions because identity matrix is always a square matrix. So you just need to provide 10. So you can see the principal diagonal, it's 1 throughout. Okay. So this was a bit about NumPy arrays. We looked at a few, and one good thing about NumPy is NumPy's random number generation powers. Okay, we can generate random numbers from NumPy. Basically, the idea behind random number generation is that there are different kind of distributions in the universe. You have a normal distribution, you have a uniform distribution, you have a binomial distribution, so on and so forth. The idea behind these distributions is that they follow a particular pattern. Every number has an assigned probability of occurring. So you can assume that if you are using a normal distribution which has a mean of 10, if you assume it to be a bag of numbers, that bag of numbers will have a high quantity of tens in it, and it will have a lower quantity of other numbers in it. So whenever you pull out one number from that bag, the probability of it being a 10 will be huge as compared to a probability of it being 100. So that's about NumPy random number generation as well. So if you specify that, hey, can you pull up 100 from a random number distribution which is centered around 10, the probability of that will be very, very low. But if you pull up 10 from a random number generation with a center around 10, the probability of that will be huge. Okay, so that's all about NumPy's random number generation. The way to do that is just like we call the NumPy's linear algebra subdirectory, we can also call np.random, and we can, you can pull out, let's say, random integers, and it will ask you the range of numbers that you want to pull out, let's say 10 to 100. And you can see it picks up one number. And if you ask for size, how many numbers you want to pull out, let's say 10 numbers. So it randomly pulls out these numbers. Okay. Suppose I want to pull out np.random.rand n. Okay, rand n. Okay. And let's say I provided 10. So it will pull out 10 numbers from a standard normal distribution. Now, when I say a standard normal distribution, what do I mean? Let's pull out 100 numbers, or let's say 1,000 numbers. If you closely go and observe, let's say 100 numbers only. If you closely go and observe this entire array, you'll realize that there'll be a huge population of numbers which are around 0, and a lesser population of numbers which are around 1. Because that's the pattern that a standard normal distribution follows. A lot of numbers in a standard normal distributions will be around zeros, and some of them very less, or very few of them will be around 1. Okay, and I leave that to you to read about the probability distribution function of a standard normal distribution. But NumPy allows you to generate random numbers. That's all I wanted to tell you. Okay, and what if you wanted to check and reshape the shape of an array? This is very important when you are trying to, for example, if your code requires you to do some matrix multiplications or dot products or whatever, you might want to change the shape of the same array. You might want to take the transpose of that array and stuff like that. So let's create an array. Okay. Let's say A1. Okay. So np dot random. Let's create a random integer array, randint 0 to 100, size equals to, let's say 10. Or let's say I provide a size of, let's say 9. So A1 is this one. So there are 9 elements. You can also store these. If I check the shape of this, it's a one-dimensional vector with 9 elements. What if I wanted to reshape it to 3 cross 3? I can do that using this simple function. Okay. So this is the way to reshape it, and I can show that as A1 3-dimensional. Okay. So this was how to check the shape and the reshaping and all. And just to tell you, indexing and slicing is the same in arrays like it was in NumPy, etc. Sorry, in strings, in lists, etc. Okay. So we conclude the NumPy part here.